嗯，有一层呢。哦，是哦，现在有 functional analysis 呢？哦，现在有 functional analysis 公关。Okay. Okay. Before we start, I want to do some motivation. I understand that maybe this course is a little bit hard for some of you. Maybe most of you, I don't know, lah, but um, just for some of you. Um, Actually, I repeat this argument to all my previous students. So, except actually, I mentioned this last in 2309. Because seems like that class will listen to the lecture, maybe because at that time you are still mentally strong or you are uh, better as a material. Okay, so you still can understand. But until you will, what I want to say is, you will reach a stage. Okay, you will reach a stage that you won't understand what people say. When I say you don't understand people say, is you are trying to dig up what you understand to understand what people are trying to say. This is what you're understanding now. But having an advantage of learning maths that you don't know is about understanding what people understand. You understand what I said? You are not using your understanding to understand what people understand, but you try to understand what people is understanding. This is a very different skill. Okay, and this can be trained in mathematics. Because in mathematics, we speak about logic. Okay, so when we talk about logic, right? What's logic in simple word? What's logic in simple word? Huh? Is what? Is a 什么？听没懂？方法 method is a method. Okay, in a simple word logic is just linking two dots together. This red line here called logic. In simple word. Okay, we're trying to put explanation. Okay, to two things. If then, okay, if this then this, why? Proof. Right. So we typically in mathematics we fill it in as a proof. Okay. Every two dots we want to make a link. Okay. So in this class here, what I want you to do is, I know in this class all of you have good self-study skill already. Okay. So this is good. But I want you to learn a further skill. Further skill is, can you try and discern what I say is correct or wrong? Okay, this skill will be useful for you to go seminar or even daily communication is very important. Okay, if for our mathematics use, it's very useful you go when you go to listen to seminar. Typically, when people talk about one topics, right, you won't understand one because it's too deep. I mean, it's too niche. Okay, so without prior knowledge, right, can you decide what he says is wrong or right or not? Okay, does it make sense? Do you understand or not? Before before doing it, you have to understand what I said first, and then only then we talk about how to execute it. You understand what I said, Eugene? What I say? Say never mind. Mm. Say again. Never mind. Way to understand what people say. Yeah, try to understand what people say without your prior guessing. I mean, you can guess, but you need to align with what people are trying to express. Meaning, don't put your own understanding. So don't put your own word into people's mouth. Don't put your own word into people's mouth. Okay. Maybe I teach like this. You say, oh, because teacher teach like this. Maybe it's not. So you need to really understand what I'm trying to say here or trying to tell you. Okay. If you don't understand, what do you do? Huh? Vice. If you don't understand, what do you do? If you don't understand what I say, what should you do? Yes, you have to ask me because it is what I say. It depends on me. Yeah. Okay. Yeah. So this is a very important skill. Next skill you need to learn. Okay, when you go into these advanced courses, advanced knowledge, it will get even harder. Okay, this is just the first hard stone only. Okay, no. Okay, for example, I give you an example. Apparently, I was approached by a student from Imperial College, London. So he will be coming back to Malaysia at the end of June. Right, so that time is around our presentation time. So I invited him to join our algebraic geometry presentation. Okay, so he was interested with my work, so he wanted to talk to me. So maybe I was also interested with his work. So I was thinking that we will make maybe a 1 month seminar, okay, between me and him. And at that time, maybe it's your revision week, exam week, but hopefully it's just 1 or 2 hours. Then if you have time, you can come. Okay, yeah. But if you look at the topic here, maybe like Eric said, our standard is not there yet. Yeah, sure, your standard is not there yet, but at least I want to train your soft skill first. Meaning you need to try and listen. Okay, try and listen what people say is correct or wrong. No need to fully understand the whole theory yet. Without knowing the whole theory, you still can discern something is correct or wrong. Just using simple contradiction implication. On the spot, you will see what's correct, what's wrong. And then from there, you learn. Okay, no? It's not like how we study in class, like, or we have to learn whole theory, only then we can go to exam, go to test. It's not like that. Test and exam is just a tool to test whether you know. It's not that you need to learn everything, only go to test. You understand or not? Yeah, don't make these um uh don't make these sequence wrong. Okay, does it make sense? Okay, so I hope when he came, right, you can come also. Okay, and I invited him to your talk also. Okay. Yeah. Okay. Yeah. So his topic is about postural homology, vehicle space, and then he told me that he is doing a lot of reading group at UK also. Okay, reading group on topological K theory. And maybe these would sound very unfamiliar to you. But what I want to show you is there's a lot more unknown, okay, in this world. Algebraic geometry is a small thing only. Okay. Yeah. Does it make sense? Okay. So try not to see this difficulty as end of the world. It's not end of the world. There's a lot more end of the world inside there. Okay. No? Yeah. So very simple. If you get stuck, get get stuck, get confused. Just ask. Okay, just ask me. Okay, just ask your friend. Ask ChatGPT. Uh, when I say ask, not just copy. You need to like check, understand what they are trying to say. Okay or not? Okay. So in my class, I won't ask you to copy and paste. Okay, so make sure you understand what you are writing. Okay. Yeah. Again, this is the only way to learn as much as you can. Right. Yesterday, Eric asked me how to study. Right. So you just learn as much as you can. Be open. Be open. Mhm. Okay. Because nowadays, mathematics is not about one field. It's not about algebra. It's not about analysis. It's not about geometry. It's about everything. I follow that we like geometry land is like almost finished being proven. All these fields get linked together already. Okay, you cannot say, oh, I just like analysis, I just want to study analysis. No, cannot. Because in future they will merge together. Okay, so you need to like master in almost everything. Maybe you will like this more, like that less lah, but you still need to polish your skill. Okay, or not? Yeah. Does it make sense? Does it make sense? Does it make sense? Okay. I mean, tear and tear, tear and sweat is necessary lah. Okay, for hardworking person. But if you know this AI guy, AI giant, Jensen Wang, so he often says that I hope you pain and suffering. Usually people say hope you a good things, right? But he will say hope you a pain and suffering. Why? Because pain and suffering will build your character. Okay, and then this character help you to grow to success. Okay, so character is really important. Okay, so in this school, we are not training you knowledge only, not just about algebra, not just about geometry, also character. Okay, can you be disciplined or not? Okay, can you learn in time or not? Can you give good feedback to lecturer or not? Yeah, I mean good feedback meaning like you can give good responses. Okay, can you interact well with your classmate or not? People or not? How do you live in this society? This is a small society here. These are way more important, right? So through studying, you learn how to live in this world. Okay, or not? Okay, yeah. Don't don't forget. Okay, you are suffering. I'm also suffering, right? If you do a lot of homework, I also have to mark a lot of homework, right? You think I'm happy to mark? Eh? I'm how to say king to mark so many assignments. But I done this on a purpose. You know what's the purpose? You know what's the purpose? I put all these assignments. What's the purpose? to suffer, then you are very wrong already. 我没有这样吃饱这样显空给你 suffer，对不对？Obviously, this will imply suffering, but more importantly, why I gave you assignment? Why is there a test? Very basic question, ma. Huh? Sorry? To train, to check, whether you understand something or not, or you learn something or not. Okay, so if you don't submit or you don't follow this rule, then I cannot know whether you're learning or not. Correct or not? Very simple argument, right? Okay, yeah. Okay, okay. Hopefully no one sleep today. Okay. Uh, so yesterday I have some typo actually. Yeah, so this typo I actually catch by Eric. So Eric also not quite sure about the topic, right? But he want to ask a question, for example. I'm not sure how many of you catch it, but at least he talked to me. So this part here, yes. Oh, sorry. So I read at least this part here. So if you look at this line here, so let's just look at this particular line here. Okay, we know that from Hubert's non-Stellensat that yesterday there's no this red line here. I said that there's this non-zero polynomial, which is a non-constant polynomial, non-zero polynomial that has empty zero locus in C2. So we can assume that G vanishes on this point. It turns out that there's a typo here. Actually, it says that there is no non-zero polynomial. And also non-constant because we want to do contradiction. Okay, that has an empty zero locus. So what point of Hilbert non-Stellensat we are using here? We're using the weak one. Why? What does the weak one say? Okay, so how does it apply here? If there exists a non-zero G, okay, that has an empty zero locus here, then you will create a proper ideal using this G. Okay, but I don't think he found this problem using Hilbert non-Stellensat even. Yesterday he also cannot recall this Hilbert non-Stellensat. But where's the problem? You first thought there's something wrong here. What's the logic you use here? Yeah, correct. Very easy contradiction. I said this one don't have zero, but suddenly I assume there is something is some vanish at some point. This is a very clear contradiction already. Without knowing, I mean, this zero locus one, I think first year would know already, zero. But without knowing Hilbert non-Stellensat, you should see some contradiction here already. This is what I meant. You don't need to go into a full theory. Okay, some statement maybe need very hard implication, but some statement just need very easy implication. Actually, almost all the time is like that. Almost all the time is like that. Very few implication that we need a very strong result. For example, this existence thinking. Okay, I mean without the second part. But you see, there's relation here, man. Then you can think about whether these two will contradict. Okay, does it make sense? Okay, in this world, usually the implication is easy one. Very few we need a very hard theorem. Does it make sense or not? If all the implications are hard, then all the proof will become very long already. But this is not the case. We only few times present long proof. Most of the time are just short proof only. You understand or not? You can think about it. Can you think about it? My claim is not all the implications are hard. Or almost all the implication is not hard. Otherwise, we have to spend whole day proving one implication already. If most of them are hard. No, most of them is short. Okay or not? So don't give up. One thing I want to tell you is don't give up. Okay, never give up. Okay, don't give up. So do you need hint for your assignment or not? Assignment 1. Assignment 1. Sorry, assignment 3. Question 1. Because I got requests from some of you. You need a hint. Okay, what's the hint I wrote to you just now? Okay. Okay. So I guess maybe most of you found some material on Bezout theorem, right? About that you need to prove this. Is it what you told me yesterday? Some form of Bezout theorem. Yeah. You don't need the whole Bezout theorem. Okay, you just need some weak form of Bezout theorem. Okay, so what you can try and prove is you can try and prove first. So okay, this one is the hint for assignment 3, question 1. Okay, so in this case, what's given for you again? One is empty set, irreducible affine variety in A2, affine 2 space. The other is singleton. Okay, because if it's finite, then you can reduce them. Okay, if you have finite set of points, then next one is infinite case already. Okay, so now what we're gonna produce is, so this is the theorem. If f in K adjoint xy is irreducible and X is an infinite algebraic set, such that, well, if you are the algebraic set, right, you are usually a V, you are staying in V of something. Okay? And then you should prove that Ix is generated by F, this irreducible F. Moreover, from here, you can then prove that X is just Vf. And then Vf is irreducible. This is the last irreducible set. Okay, but to prove this, maybe you need a lemma here. Okay, so if Fg in Kxy have no common factors, then V of Fg equals to Vf intercept Vg is at most finite set of. Okay, so well, you see, this is lemma theorem, right? So there's a sequence here. So meaning before proving this lemma, right, you should be able to use this lemma to prove the theorem. Okay, so try to think about that and then try and prove this lemma. Okay. Okay. So yeah, this is why I say this course will be harder because not everything maybe I will tell you. Okay, so maybe you need to prove something extra. Okay, find some wrong method yourself. You need to prove something extra. It's not obvious like in other classes that, oh, I teach you this definition or just use this definition and then play come already. Okay, so because this is the advanced course. Okay, so it's not as direct as the easy course, the fundamental course. Okay. So yeah. Okay. Maybe this is not the only one way, which I want to stress here also. Okay, but this is one way. Okay, so that's why yeah, actually yesterday Ari also asked me a question, right? So matter is very important. Matter is important. But what I want you to understand is concept is even more important. Once your concept is right, your method will be right, no matter what method you use. This is how people come up with new things. So maybe this person logic is clearer, shorter. You understand or not? Then you will provide a new path. Then people will follow you. Okay or not? Yeah. So don't obsess with method, I would say. Don't be obsessed. I mean, when I was an undergrad or postgrad, I was also like, oh, this lecture didn't tell me how to do, then I'm done. I'm doomed. Finish. So I need to go and ask senior. I even asked postdoc. I asked the postdoc from the lecturer because that lecturer is not friendly. So I go to ask the postdoc. I mean, this is one way to learn, but at that time I was quite spoon feed without knowing that I like spoon feed. Because I was grown in the Malaysia education, then you understand, right? When we do SPM, we just do a bunch of questions, then we can get A already. Seriously. We just do a bunch of light questions, then I can get A already. I thought that I know how to do. Actually, I don't. Okay. Yeah. So, listen is very important. Try to learn this word, listening to people. What people say. Okay, another thing that I mentioned wrongly, I keep confusing, is about the complex analysis part. The complex analysis part is about this part here. That I was trying to link algebraic geometry to complex analysis. We are not quite at the Lear-View theorem yet. We will soon do the counterpart of it. But yesterday, what we proven was the locking on the open set of non-zero complex number is the same as the locking at the whole complex number. Where is it now? Not just complex number, it's a complex plane. Where is it? Where is it? Yeah, this one. Yeah, this one. Okay. We proved that. What did we prove here? So we proved that the locking on a complex plane, okay, throw away the origin, is the same as the um, locking on the whole C2. What this means was if you have a regular function on a punctured complex plane, you can always extend it to the whole C2. Is the same root. Or you can extend it. So this is what term in your complex analysis, the removable theorem. Okay, by Riemann. Okay, if it's a isolated singularity theorem, then you have this limit here, and then you can remove it. Okay, you can remove it, meaning you can further define a point at that point to make it a full uh, unit, and as you need just continuity, right? Yeah, I think just continuity here, to make it continuous at that. Okay. Yeah. Okay. Yeah. So the discontinuity point here caused by singularity. Right? Caused by singularity. So for example, right, what are the removable singularity? For example, let's say this 1 over s cubed. 1 over s cubed. Is it 1 over s cubed? Let me think. How does 1 over s cubed looks like? 1 over x squared, 1 over x cubed. Like this. Then this is not my example. I was trying to say like something like this, but this one is s cubed, huh? Sine x over x. Sine x, let me think, sine x. Sine x over x. Oh, sorry. Sine x over x. Sine x over x. Let me think. Sine 0 is 0. Okay, this one good. Okay, so this one is like this, right? If I'm not mistaken, like this, right? Or the other way around. What's this shape? What is the shape of this? Okay, when s get larger, should be smaller, right? Like this, right? Hey, I mean this one not good, eh? I think what is good, huh? There's one you can feel, there's one you cannot feel. Anyone remember? Or x square, x, x square, x, x, x is crazy, you can cancel it. Huh? X sine 1 over x, you can cancel it. Oh, like this. This one. I think this one like that. Is it? I remember I did this in MA, but I forgot which one. This one. Is it this one? I think it's this. I think one of them you cannot feel, the other one you can feel. You can fill up this singularity point here. Because it's not defined there, right? If you look at sine 1 over x. Okay, but the limit from both sides is going to 0. Then you can fill it. Okay. Does it make sense? The function is if surf is not defined as 0. Okay, because 1 over 0 doesn't make sense. But if you look at the limit of that function, right, both sides will approach 0. So you can fill this point in piecewisely as 0. So what's this? I remember the shape, but I can't remember the. I can't remember. I think I can't remember. Okay. I think how we prove that is using squeeze theorem. So I think it's something looks like this. Not like this. Huh? I remember we proved this limit using squeeze theorem. So what's the full form? What's the full form here? Anyone remember? Yes, actually. What's that? X sine over x, right? Okay, then okay. That's right. Actually, you can prove this limit using squeeze theorem here. Okay. Yeah. Okay. All right. Yeah. But we will mention a Liouville theorem later. Again. The one that we mentioned in class yesterday about entire function. Okay. So yesterday we mentioned about function that cannot define everywhere, right? That don't define everywhere in our variety. Okay, we call these rational map. Okay, rational map. So let's see. So let's look at this example here. Let's look at this example. C1 equals to a curve that satisfies y squared minus x cubed. And let's look at this curve here. So this curve here would have a parameterization, right? So we will have a parameterization from A1 to C1, okay, which is sending t to t squared t cubed. Well, this is kind of fancy, right? But I mean, in calculus 1, what we wrote here is just fr to r squared, and then t sending to t squared t cubed. Okay, basically, this is a parameterization. Okay, but we restrict to C1 because this parameterization here will satisfy the equation above. Okay. So last time we mentioned that this is not a isomorphism. Okay. So we know that the ring of A1, or you induce an algebra map that's also not an isomorphism. Okay, so the isomorphism on variety induce an isomorphism on the coordinate ring. Why is it not an isomorphism of variety? If you want to look for the inverse, how do you find it? How do you find the inverse? Okay, that's not the general argument. I gave you general argument last time, but one of the possibility is like you take y over x, right? T cubed over t squared, then you get t. But y over x, this map, right? You need to divide by x. So division will cause problem. So it's not defined at the point x equals to 0. Okay, so that map is not a polynomial map. Okay, not a polynomial map. It's not. Yeah, okay. But I think last time I wrote in the lecture note in general why it can't be a polynomial also. Okay, you can check it out. But we devised a very convenient things called rational function, rational map, right? So if you look at the restriction, f from this quasi-affine variety, A1 take away the origin, and then C1 take away the origin. Okay, in fact, it is an isomorphism of quasi-affine, right? Okay, so y over x is not polynomial, but it's a very nice regular function, okay, or rational map, or rational function. Okay, so in this case here, similarly, we will use this. We will get an induced map from this f. Okay, from KC1 to KA1. Okay, obviously, maybe you want to check whether this f is a dominant map or not, but it should be. If it is a dominant regular map, then it will induce this um, map on the k-linear homomorphism here. Okay, so what's the k-linear homomorphism here? So if you have a G here, where do you send it to? Basically, you just send it to the pullback of F. It's the same. It's the same construction. Okay, but in this case here, we talk about field of function. Okay, yesterday we talked about field of function. Yeah. So we can ask whether this is an isomorphism or not. Okay, is this an isomorphism or not? Okay, this is an isomorphism or not? Hmm? Yeah, why? Why is it isomorphism? So you need to check whether it's surjective or injective. Sorry, it has an inverse. From here, I think you should see that. Okay, first of all, it's injective because it's a map between field. Yeah, every homomorphism on field should be injective. Subjective. So that it's subjective, what do you need to do? What was that here? Huh? And a pre-mesh for everyone. So let's draw this diagram here. So we got A1, okay, to A1, and then we're going to some A1 again. This is the whole thing. Okay, so if I gave you a A1K to A1K map, what should you do? Why do I put a G here? So I picked this specific G here to tell you that this map will get you T. Why did I write this? I forgot already. Why did I write this? Mm-hmm. Mm-hmm. This is an inverse for F, right? This is an inverse for F. So what you do is you just pre-compose again. Wait, let me think. So let's say if you have a general F here, right? How do you get the G back? So who gets sense to this H here? HG. HG. HG will get sense to, wait, yeah, I think this word, right? Right. So HG, how to sense to H? Because H is equal to HGH, which is H on identity. Does it make sense? Sorry? ERC 你讲 composite 啊 Yes. So for every H composed G is the image. Let me think, is it correct or not? H is going from where to where? H is a map from A1K to A1K. Then okay lah, I think, because you pre-compose with G, so you start with the right domain. Yeah. Okay. Yeah, I think it works. Yeah, because G go from C1 to A1, and then H go to A1 to A, and then H is going from A1 to A. Okay. Okay. Does it make sense? Okay. Does it make sense? Got question? Got question? Feel free to ask. Feel free to ask. Don't think of asking question is like challenging. Maybe I know some lecturer will think of it as a challenging. You know what's challenging 不是很难的 challenging 是挑战的 challenging. Yeah, like fighting. It's not fighting It's just discuss. Try to be open a bit. Okay. 你错没有I'm okay one. Okay. If I'm wrong, I'm okay. I hope that you are okay. Because the point here is to learn. It's not like to dictate you or force you to do what. You don't want to learn, don't want to learn. It's okay one. But I want to find someone who want to learn. That's okay. That's why I come back to Malaysia actually. If I don't come back to Malaysia, actually I can stay in Australia, you know. Actually I can, if I'm not working as a scholar or postdoc or in Max, I can easily work in McDonald's, you know. I can easily work in the farm, you know. Did you see the news or not? You will earn more actually than working most of the job here, you know. Just go and pick apples maybe every day. Yeah, correct or not? Okay, the point is I want to come back and share this knowledge. Yeah, otherwise, I can just stay there and then get a PR and then maybe live a very decent life already. Right. I come back here, 1 month salary also cannot get an Apple phone. For what? I work here. You understand? Okay, so just trying to give me some feedback. Okay, whether you understand or don't understand. If you don't understand, we try and work out. Okay, how to make you understand. Not by forcing, but by making sense. Okay, so first, F is subjective. Okay, and being a non-zero field homomorphism. Field homomorphism is always injective. This is some very basic fact to prove because basically there are only two ideal you can consider in field, either everything or even zero. Okay, so if your kernel is everything, then you are zero map. Then the only case if it's non-zero field homomorphism, your kernel must be the zero ideal. And so, okay, so we will have that K A1, the field fraction of coordinate ring of A1 actually is isomorphic to the field fraction of coordinate ring of C. Okay, so what do you see in this example is you get an isomorphism in field of fraction, but not the coordinate ring. Okay, so it might be not the same at the polynomial level, but it will be the same at the rational level. Does it make sense? And then this corresponds to what? To a uh, to a bijective rational map between variety. Where rational map here just correspond to these regular function. Okay, might not be defined everywhere. At few points we cannot check. Never mind. Okay, so this differentiate between isomorphism and birational. Okay, later we'll define birational, but this will hint to a term called birational equivalence. And you have this rational map going back and forth. So that's a birational. Okay. Later we will discuss this setting in a more general sense when we go to a projective variety. Okay. Okay, no? So this rational map is not defined everywhere. But if you look at the field of fraction, is look nice. It's an isomorphism in the algebra side. Okay, and in the variety side, maybe at some point we don't know how to handle, but that's fine. At a large scale, we know how to handle. It's a dominant. Dominant means what? F of dom F must be Zariski dense. So you actually check at most point already. Most of the point already. Zariski dense. Most of the point you already check already. Okay. Okay. Maybe you can ask a question as Zariski dance can include throwing 1 point or throwing finitely many points or throwing countable many points or throwing uncountable many points. Okay, maybe you can ask this question. Okay. Okay, but that's not the subject now. Okay, next. Oh, 449 already. Let me think. 1, 2, 3, 4, 5. 449. Can I finish one proposition and one corollary before we break? Can? You got the mind brain power to continue now. Can I? What? You still got power to deal. Okay, good. Okay, good. Okay. Okay, thank you. So, okay, let's look at this specific quasi-affine variety here. So let's take any affine variety, B, okay, and then take the F, okay, from the coordinate ring of V. Let's define the following quasi-affine variety here. So a very obvious one is Vf equals to V take away the zero set of F, okay, which is all the point in V, such that Fp is non-zero. Okay, because you look at the complement, okay, of Fp equals zero, because there's a zero set of F. So the proposition was yesterday that we want to achieve here is this specific quasi-affine variety here, Vf, is actually isomorphic to an affine variety with coordinate ring K of Vf. I call it K of Vf here. I haven't really defined yet, right? I haven't defined this here, right? Okay, maybe we defined it. So we define this coordinate ring as K of V join F inverse. Uh, it's also the same as talking about localizing KVF. Okay. So localizing here, you need to look for the what's that called? Multiplicative system. Right, multiplicative system. So the multiplicative system here is this multiplicative set of that. So look at the power and then look at the complement. Okay. So maybe this proposition is very good if we compare it to a example first. Okay, let's compare to an example first. Any example you can thought of on this proposition here? An open set but isomorphic to an affine variety. Okay. One example you can see was if we look at this affine variety, right? So let's draw one affine variety here. Oh, well, I think I learned this in my A level. So what's this affine variety here? Draw it properly. And let's draw this asymptote. Okay. So there's two asymptote here. Okay, there's two asymptote here. One is zero. One is y equals 0. One is this point here. This point, where should we let it go? We should let it be. Let's call this line. Let's use algebraic geometry language to call this line. Let's call this v of x minus 1. So I think you would know that what's the function, okay, that define, or the polynomial that define this variety here. Anyone know? I think, how about Larry? Larry, yeah, what's the polynomial that define this W? Okay, let's give you coordinate first. This one is x, this one is t. Don't use y, I use t. How do you get this? Huh? How do you get this? So if people already get this, you don't know how to get, right? You can work backward. Okay, if you work backward, what do you get? Tx minus 1 equals to 1, and t equals to 1 over x minus 1. I think everyone should be familiar with this, right? It's the shifting of 1 over x. Right, 1 over x look something like this, the second and the third quadrant. So you shift it to the right. Okay. Okay. But if we project, if I project these two lines down into x-axis, right? If I project them into x-axis, what do you get? Huh? Sorry, line, a line, a line with a hole. Okay, a line with a hole, correct. But a line with a hole is a open set. Okay, because it's a complement of a point. Okay, a point is a R5, right? Okay, so this projection will form your isomorphism. Okay. Okay, so this is observation you make here, but how to do it general, this is what this proposition tells you. And this is what this proposition tells you here. So how we're going to prove this? So actually the trick we're going to use here is, again, the Rabinowitz trick. Okay, it's like how we prove the Hilbert non-standard result. Okay, so how do we do this? So first of all, let's let J to be IV. What's IV here? Okay, because we started with an R5 variety, right? So we got an IV here. Be the ideal of the variety V, A, and K here. And let's let the big F in the polymer ring such that when we restrict to our variety, it is just the little f. Okay, because this little f stay inside the coordinate ring. Okay, so it's a polynomial. Okay, it's a polynomial. So maybe it come from a bigger polynomial, but that's fine. So what we set here is, so how can you imagine about this f? Because f restrict to v is f, small f, meaning what? It could vanish on the point in v. So meaning this f could be f plus some element in IV. Okay. Okay, then since we want to use the trick, right? So let's define JF. So JF here is what? Because we got an ideal, we got a function here. So what's the Rabinowitz trick we used last time? You enlarge the ideal with something act like a inverse. Okay, so meaning we generate this JF using J and the inverse of J. Okay, after quotient is the inverse. Okay, so TF minus 1. After quotient, then T is the inverse of F. Okay, so we adjoin this T thingy up here. So what we claim is, the claim is, and we claim that VF actually is isomorphic to W, where this W is the V of this JF here. Okay. So well, this isomorphism is a birational, the rational isomorphism. So you could define some map that's not everywhere. So you could have a regular. Okay. So what's the map here? So you need to produce two map. So there are two mutually inverse morphism. There are two mutually inverse morphism. Okay, so let's write down what you want first. So first one will go from W to VF. The other one will go from VF to W. Okay, so how to go from W to VF here? So W live in a space of n plus 1 affine space, right? So you have n plus 1 coordinate to take care. So which VF you need to go to? Very easy. Just throw the T away. Because your VF is coming from n affine space built up by x1 to xn. And then how about to go the other way? The other way, how it works. So if I start with n coordinate, where should this go? Okay, obviously you want to create your T back, right? Okay, so how to create your T? Using x1 to xn. How to create your T? Not enough, right? You need to use 1 over f of x1. That's it. Right. So try and compose them together. Do you get identity or not? So if you go this one, go here, throw T, then go back up to n coordinate. Right? Okay. So if you start here, and then you go here, and then go here. So is this the same thing you started with? This is the same thing you started with. Is T equals to 1 over f of S1 until Sn or not? Are they the same? Is T equals to 1 over f of x1, xn? Are they the same or not? Why? NgeKieSeng. Why TF minus 1 equals 0? Because we are looking at V of JF. Okay, this 1 TF minus 1 is an element there. So I need to make this equal 0 inside W. Okay. Yeah. So if you use this technique, this is exactly how we find this. How we find this two variety here. Right, you see there? We inverted x minus 1. Okay. 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 So last thing here is the corollary. The Zariski topology actually has a basis of affine set. Okay, has a basis of affine set. So the basis here is the topology basis. Okay, the basis in topology. Because every open set in V is a union of set that's of the form VF. Okay, and then this VF will form the basis. Yep. This V, is it a affine variety? Yeah, yeah. Okay. So last time we mentioned that the the GLN is not an affine variety, right? Because the polynomial that is satisfied is determinant not equal to 0, right? GLN. Okay, it's not an affine variety, but it is a quasi-affine variety, and it is isomorphic to some affine variety. So you can almost treat it as an affine variety. So you can write it as some VF form. This is a VF form. I think it's a union of these VF, not just one. Union of this kind of VF. You need to satisfy some polynomial equal to 0. A bunch of polynomial equaling 0. Yeah. Okay. Yeah, any question? So this is about affine variety. Later on, we will move to projective variety. In projective variety, similar story will work. Okay. Actually, later we will see that projective variety will include affine variety. So in the end, you just need to talk about projective variety. Everything is just something in the project. Okay. So let's break until 516.哪个 hint？ 哦，那个 hint， 那个 hint 啊，就是 prove 那两个 statement，然后就告诉你那个 infinite set 是一个 irreducible set。这样个。
不能确定问题。
Yeah。
最近Quasi-affine题的时候，它那个 open 其实是 subspace 的好友的。
你可以，你说 Quasi-affine 啊？你可以。
definition 里的 open 是 open in 整个 space 还是 open in B？
我想一下。Well, I mean like， 我想一下。
但是像
啊，是啊 affine variety， 但是他把 affine variety 看成那个 affine space 的一个 subspace， 所以就。
所以其实是只要看它是一个 open set 的硬币。
Well， 你这个问题哈，只是我有想过这个问题啊，后来好像它最重要的点是你最怕的东西是发生在 boundary 的时候，这两个才会不一样。
Yeah。
但是就是 like， 如果你已经把它看成一个 space 了过后，这样的话，好吧，你应该是看成 subspace 这样子讲。OK，yeah。它如果只要不影响你的 boundary， 其实它们两边都是一样的。但是就是能够想象嘛，就是来那个 half open interval 嘛，那里的 open set 是什么？如果你没有动到那个 boundary 点的话，里面的 open set，
对啊，
在里面 open 跟在外面 open 是一样的。那重点是那种好像来0到 0.5 到1的怎么办？
对。
啊？
哎，我
restrict to V，
就是大 F，
就是整个大 F 是定义在这个所有的 variable 上的，但是它把它 restrict。
Actually，
polynomials 跟它 idea 东西都是 principal idea。
KX 是 principal ideal domain， 但是 KXY 好像就不是啊。KX 是 principal ideal， 如果你 feel 是 ，Yeah，I mean K 是 principal。K 是没有，我们只有证过 feel adjoin X 是 principal ideal domain。feel adjoin XY 的话就
也就是说，我们应该不是
对呀，
应该不是。
啊对，是 subspace 的问题。
让我再想啊。
对呀，affine variety 是 Quasi-affine variety， 因为我说
啊，因为 affine variety 一定是 open，
一定是 open， 因为它是整个这个 set， 整个 set 一直 open。就我考虑到 subspace， 你什么 affine variety 什么意思？所以相对来讲啊，
affine variety 中文是
对，所以
affine variety 的中文
Quasi-affine，
我不懂哎，我不懂哎。
反射处，
你这个
反射处为什么是反射？
反射是 affine。
对，为什么反射是？
放 那个模仿的仿，
模仿的仿式。
哦，模仿的仿，
里面，
模仿的仿，
然后再讲
仿色是映射。
面音
那个
OK，choose variety。好，那个仿色为什么是 alpha？
也你去
我没想完，你却想到这个。
这个关系。
然后那个 Quasi 那个是四仿式，是错。
哪个？
Quasi-affine
你
variety 是
要找他的 complement，
就是那个提手旁四这样的意思。
其实你懂这个还表示 basis 是什么？
哦，模拟啊，模拟。OK，这个 make sense。
find set
就
对，
这个是为什么发现这四仿式？
不对是这个像是他有一个他讲我的这个是第一个是 basis find set 什么意思？就 find
你是说是 affine 是什么哈？还是我少了字？应该是 affine 还是 algebraic set？affine affine。喂，如果是跟下来的话，上面是什么东西？variety 应该不是 set 吧？不是 variety 吧？
是一个 affine variety。
variety topology 用 affine variety 做出来，应该是 affine variety。我想想，还是 affine algebraic 啊？
但是这个就是 the landscape topology of B affine variety has a basis of affine varieties。这个大的 affine variety 下面是由小的 affine variety 组成的。
等一下，喂，我等我想想。
一整页
affine variety 怎样？
affine variety
对，应该是 affine variety，因为我应该想讲的是这些 quasi-affine variety 是会 form 它的 basis，但是 quasi-affine variety 是 isomorphic to affine
这个
variety。
是另一个空间的 affine variety。这个空间的 quasi-affine variety 是 isomorphic to 另一个空间的 affine variety。可是我们想这个 topology 里面的时候，不能把它当成 affine 来看，要把它当成 quasi-affine，因为我们有它是 isomorphic to 另一个空间的，你可以多一个维度，多一个 f v。它是
OK，
另一个维度的 affine。这个空间是 quasi-affine，所以这一个里面的第一次由 quasi-affine 组成的，但是不能讲这个是 affine，我们还在这个空间里。是。
给我想想。
这个结论是他讲到的点是什么
？OK，给我想想。OK，等一下我再重复一下这个东西，等一下我再重复一下。我们需要几点来着？我需要几点？那需要几点？
按理说应该还有好的，因为你基本上发6分。
他把那个
OK，再等一下。
这个 VF，然后再找
affine set 是什么？
对，
哦，
应该 affine variety 吧？
是那种
看一
X
下
X 数学这个样，
字写错。
这个就是个但是这一个是我扣就是
然后右边那个
这一个为这个为 domain 的全部这个样子呢，其实是跟我本来的
你选
这是个人这些你是属于分子，然后这个就是粒子，然后
对
这三个
射手，然后就打。
啊
扣面怎么 join？
？join 一个。哦，之前有讨论过，就是 like 你可以乘 inverses 去你的 function 吧，你就可以乘 inverses 去你的 function 吧，没有什么什么怪怪的。 它就乘 inverse 去，可以乘你的 f inverse 去你的因为我 invert 它了啊，我 invert 它，我的它的 ix 是 invert 掉那个 f 啊。Okay, I think we start now. Okay, just now, this word here a bit confusing, right? So, well, first of all, it's a basis of it should be a basis of quasi affine variety, right? Okay. Uh, but because how to say so let me think. Okay, so the first time I thought about this was because this RSP topology is closed topology, right? Then your basis, well, you can understand it as an open topology, then you look for the open basis, right? I think at the same time, you also can look for the closed basis, right? So, but the problem here is, how can I say that just now when we build this isomorphism, right? Actually, you need to enlarge the ring. You need to enlarge your ring, okay? I think the point here is, if you go through this isomorphism, right, you should be able to place your V in this large ring as well. Okay, so first statement is the derivative topology of V has a basis of quasi-affine variety. But what I want to say is through this isomorphism, I think you can realize this quasi-affine variety as an affine variety. But the problem here is, but the affine variety there was sitting in a larger affine space. But I guess you can place your, you should be able to place your, okay, let me think, is it possible? You should be able to place your variety inside the larger affine space also. This help.
Define as a sub-variety of in a larger F.
Yeah, but does this help? Yeah, that's what I meant. But does this help or not? So if I put my variety in a larger affine space, this help? Yeah. Yeah, topology basis, yeah. Yeah. So oh no, because I instead of phrasing it as a quasi-affine variety, right, I try to phrase it in a affine. Actually, not affine set, just affine variety. Sorry. You see, no problem. The problem here is the isomorphism we used just now. The affine variety that we proven is sitting in a larger affine space. I don't know if you remember this picture. Okay, this quasi affine variety is sitting inside A1, right? But if we want to make it an affine variety, it should sit at a larger space. I don't know. So how can you use a larger thingy to like become your basis? It's sitting in different space, no? Does it make sense? Okay, they are sitting in different space. Then sorry. How to see? Yeah, let me think. I think we cannot just put our V at a larger coordinate ring. If you look at, I mean, in a larger affine space, if you look at this case, right? If you put this line back to this A2 thing, it's still a line. But then how you put this affine variety into your line? Maybe it doesn't make sense. Unless the only way to make sense is you need to come back to your original V. You need to project it back. something like projection. But in this case, maybe don't phrase it like that. Don't phrase it like that. Just forget this. Put it as quasi-affine varieties now. Yeah. But not quite trivial. Well, yeah. So yeah. Mhm. Yeah, at first I was thinking like I want to link it to this part here, then maybe actually it's not corollary because in this proof, right, actually before proving it, right, you need to use this statement here. So actually there's one statement I'm trying to skip here. So what's the statement? Let me see. So actually there's one statement require proof here. So every open set in V is a union of a set of the form VF. Okay, actually you need to prove this. This plus the previous one, I was thinking like combine to this, but maybe not. This is just a theorem. Okay, maybe you need to prove this claim first. This claim is like a basis proof in topology. Yeah, you need to show that this quasi-affine variety add like a basis element. I will try and add this line into the notes later. I'll add this into the notes. Okay, I'll add this claim into the note. Later, I'll prove it for you. Okay, let's move to the next part. Is the category of projective variety. Okay, so you will expect a similar setup, okay, for affine variety. So we go through the object first, okay, what are the projective variety, and then we talk about map between them. Okay, and then the last map we talk about is rational map also. Okay, then this rational map here, later we'll deduce the theorem is affine variety. Quasi-projective variety is isomorphic to affine variety. Then we can go from affine variety to quasi-projective variety. And then just talk about quasi-projective variety as a whole. Okay. Well, I think should we motivate? I think you motivate enough already, right? For projective space. Okay, so what are the nice thing about projective space? Since we have spent time on projective space already, what are the nice thing there? Every pair of distinct line will intersect. Okay, so there's no parallel line inside projective space. What else? There's some statement maybe not useful for you now, okay, but in general, if V is a projective variety, let's say in P2, okay, defined by the degree D polynomial, then this projective variety actually is a manifold, and then it's an orientable surface of genus D minus 1 choose 2. Okay, maybe it's useful for some of you that learn differential manifold. More generally, right, if you define a projective variety using same degree, okay, and then both of them are manifold, then actually they are homeomorphic in the Euclidean topology. Okay, so if you define the same degree in Pn, then if they are both manifold, meaning they are differentiable, not differentiable, locally homeomorphic to Rn, right? Just locally homeomorphic to Rn, then actually they are homeomorphic. Homeomorphic is the notion that we introduced last week, right? In general topology. Meaning what? U is an open set in one if and only if f of u is an open set. Okay, so you can transfer open set across. And then the last thing is every projective variety is actually a compact topological space in the Euclidean topology. Okay, so from the setup that we prove very in front, right, we show that the projective space is actually a completion of affine space. Yeah. Okay, so let's define a general projectivization. Okay, so let's let V be a finite dimensional vector space over K. Okay, so we'll define what is called the projectivization. Okay, projectivization of V, so PV here. Okay, so this is defined as, this time we straight away define this as a line in V through the origin. Okay, this definition makes sense because vector space always has a origin, 0 point. Okay. Okay, in this course, maybe don't confuse origin with a 0 point here, because sometimes we take origin not as the 0 point. Okay, so the most important is this 0 here. Okay, the 0 here. The 0 inside of vector space. Another equivalent definition as what we see last time was, we can take the point in V, take away the 0 point, and then introduce the equivalence here. Anyone can remember what's the equivalence we introduced here? Huh? Very first few weeks. Yes, so as long as you have a scalar, non-zero scalar such that U equals to lambda V, where lambda is the non-zero scalar here. Okay, as long as they are living on the multiple of each other. So meaning they are on the same line, okay, multiple of each other. So here, although we haven't introduced dimension in general, but we will define the dimension of PV, right? It's defined to be the dimension of V. So dimension of PV will be defined by dimension of V minus 1. Dimension of V is quite obvious, right? Because it's a finite dimensional vector space. So we know the dimension. Okay, so just dimension V taking minus 1. Minus 1 also makes sense, right? Because we consider the line. Okay, line in V. Okay. The other terminology you will listen is actually PV is the projective space. Okay, projective space associated to V. Projective space associated. Okay. So in particular, if you consider a tangent space, right? Tangent space is a vector space, so you can projectivize your tangent space. Okay. Does it make sense? Okay. All right. So some notation here. Sometimes we'll write Pn or Pnk. What is this? This is just P on K to the n plus 1. Okay. So in fact, we introduce a more general projective space. Okay, maybe recall some fact that you have know before. For example, what's the projective space correspond to R2? Okay, so what's R2? So you go to your R2, right? You look at all the lines through the origin, okay? And then last time we decided that, what is this? So where are the distinct member here? So you just take it from the upper half plane, but the left and the right horizontal line actually stay on the same line, right? Okay, so in the end, actually, this is like homeomorphic. You can show that this is homeomorphic to circle. Yeah, which is S1. Okay. How about P2R? Okay, so let's say we start with a 3-dimensional space here, and then we look at all the line passing through the origin. Okay, where are the distinct point? Huh? Plane, is the plane enough to capture all the distinct point or not? Is it enough to capture all the distinct? Huh? How about the line on the XY plane? It will be parallel to this plane, right? Okay, so in fact, you still have a circle down here. Okay, so this is the decomposition that we made last time, right? So basically, this is R2 union P1R. Or last time, the language we used was A2, right? A2 union P1. Okay. Yeah. Why the previous ones is S1, not half of it? Because this line and this line is the same, right? This and this line is the same. So, you should be able to close it back, right? I think. Yeah, you close it back. It's a loop. You close it back, right? So you here, close back. It's the same line. I don't know. If you look at the open set around here, is the open set around here. If you look at the neighborhood around here, the neighborhood around. It's a loop. Hey, Syed, can you explain why this is a loop? Why is this a loop? What? Because what? Now what am I? Endpoint of this line. The starting point and the ending point are the same. Okay. Yeah. It's his FYP stuff, so I asked him to answer. Okay. 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 Continue. So let's define this. So let's let pi from v/0. So this is a vector space, not variety. Vector space. Take away the origin to PV. Okay. We'll call these residue map. So in this, when I write these, right, it should appear in your mind that this is like a quotient map. Quotient map? No, not a quotient map, but a map into quotient. Map into quotient, right? Because we realize PV as what? What's the other definition? This is V/O having a equivalence. Okay. So, um, so, so, so we define the homogeneous coordinate. Okay, which is S0 dot dot semicolon all the way up to xn. Okay, is equals to the image of this map here. Okay. Okay. Note that immediately you should see some problem here. Immediately you should see some problem here. What's the problem here? Yeah, what's wrong with the well-defined stuff? What's wrong with well-definers? What's wrong with well-definers? Eric. Okay, with representative. Okay, so they might look different, right? But they should stay on the same point. Okay, so we'll remark here that actually you need to identify those points. So we'll say that this are only well-defined. Only up to multiplication by a common scalar. So because on the same line, we want this point to send to the same place. But if you follow this definition blindly, right, you just take your coordinate, put it in, replace your comma with your colon. But the remark here is we actually treat it the same. Okay, if they are differ by a common scale. Okay, only well defined up to a common scale. Okay. Yeah.
Treat the coordinates as an equivalent, that is already well defined.
If you treat the coordinate as an equivalent class, it's well defined. Oh yeah, okay, sure. Okay. So right, okay. So okay, you mean that if we consider this equivalence relation in, then it's well defined. Okay, yeah, you are right. Yeah, right. So why we can treat it as a multiple up to common scalar is the same because there's equivalence here. Okay, otherwise it's just changing comma to semicolon, that's all. But if you stay in the right place, this right place here will help you eliminate this common scalar here. Does it make sense? Okay. Yeah. So this map, if you just plainly look at this map here, it's only well defined up to multiplication by a common scalar. But this is exactly what this equivalence relation help you to do. Make sense? Okay. Okay. Let's see. Let's see if there's some interesting stuff to do. Okay, actually, I prepared something on how to decompose this PN, but I think this is similar to what we have did before. I just put it in the notes. And if you want to look at, let's say, projective subspace, okay, so meaning if you have a vector space, you can look at the subspace, right, of your vector space. You also can projectivize that vector space, subspace. So what's the relation between projectivized subspace and the projectivized vector space? Okay. So I guess let's see. A very maybe interesting thing that you can relate to what we learned is this. Let me write here. So let's put a lemma here. Let's say if I projectivize my subspace W1 and W2, okay, be projective spaces of, let's say, an n-dimensional projective space EV. Okay, suppose that the dimension of EW1 plus dimension EW2 is greater than n, greater or equal to n, then actually PW1 and PW2 will intersect. Okay, does it make sense or not? So your PV, okay, only have dimension n, but the total dimension of these two projective space is at least n. Then this means that they should intersect. Okay, so maybe this proof, maybe we can try and write it out. So what is dimension of W1 plus dimension of W2? Hey, wait, let me see. Am I doing stupid stuff here? I guess I'm quite stupid. I don't want P to intersect. I want W to intersect. Actually, let's see. Wait first. Let me see. Okay, so let's try and write down this proof first. W or P? Let me think. Because this proof is weird. Let me think. So let's say, okay, well, I mean, if in PW1 intersect with PW2, obviously W and W2 intersect, but okay, I think it's fine. I think we are fine. Okay, I think we are fine. Okay, so I think we are fine here. So let's talk about this first. I think we are fine. So, so if I look at this two dimension, right? This two dimension here, the claim is it is greater or equal to n plus 2, right? Because we define the dimension of PW1 as n minus 1. Wait, okay, so if you are not happy, so let me write down first. So, well, this is a dimension of PW1 plus 1 plus the dimension of W2 plus 1. Okay, but by assumption, the two dimension add out is 2, is n. So 1 plus 1 is 2. Okay. But what? The dimension, but I can write it as n plus 1 plus 1, right? Okay, which means this is the dimension of V plus 1. Okay, so this implies that W and W1 should intersect at least at one line, one more dimension extra. Okay, so that means in the projective space that intersect, because projective, yeah. Okay, and then this would prove that two lines in the projective plane always intersect. Maybe this is one way to get the axiom by above. Okay. Maybe this probe a bit sneaky. I will just define what's the line is, what's the space is using the dimension. Maybe you will ask, hey, why define dimension like this? Because circular again. Yeah. Okay. Right. I think that's it for this part. Let's go to projective variety. 5 more minutes. Okay, let me go. Projective varieties. Okay, so we got a projective space now. Then we're going to define what the projective variety is. Okay, so how about let's do some motivation first. So let's motivate our definition. So for example, let's look at just a small polynomial ring, let's say KXY here. What we notice is let's say we look at the zero set of y minus x squared here. Okay, we know that 1 is inside here. 1 minus 1 squared is 0. But not whole line is inside there. For example, 2 is not in there. Okay, because 2 minus 4, not 0. But let's say, however, if we like try to homogenize, and Adrian tell us how to homogenize it. I think this is your talk, right? Variable. How to add it? Add where? If I want to homogenize y minus x squared, how do I add? Can I add x squared or not? Huh? How to add? Forgot already. So one thing you need to bear in mind is I want to keep all the monomials same degree. Okay, so this extra variable should help me to get to the same degree at every monomial. So for example, 1 is degree 1, 1 is degree 2, right? So you might want to increase the degree 1 to degree 2. Okay, so you put the extra z there. In this case, what can you see is, what's the 0 point here? If you want to look at xz minus x squared, what's the 0 point here? Can you find an easy 0 point here? Yeah, 1, 1, 1, okay. But in fact, you can check that actually KKK will work also. Okay, so this is a homogenizing polynomial means later we will either we will do it in class or either I make it a tutorial question how to do it. So basically, if 1 point is a 0 set of this homogeneous polynomial here, then the whole line will stay inside. Okay? Yeah. Right. So you can see that when we try to homogenize the polynomial, right, that's at the expense of adding one extra variable. Okay, so you are considering the point in the larger set. Okay, but can you go backward or not? Okay, you can go backward by letting your extra variable to be 1, constitute be 1, then you can go back. Okay, go back to a previous. So meaning, you look at like the intersection, okay, intersection of this new variety here with z equals 1 line, and then you can recover your previous variety. Okay. Okay. I still got time. 2 more minutes. So definition. Let's let SNK okay to be the coordinate ring of kx0 x1 to xn. So note that there's a difference here. Why I don't call this A? If I put an, right, it just have n variable, but now got n plus 1 variable. The extra one I put at s0. Okay, extra one put at s0. And a polynomial f inside x and k here is homogeneous of degree d, okay, if it is a sum of terms a10 up to ai0 up to in of s0 to I0 up to xn in with the sum of ij equals to d. Okay, so you need to make sure that every monomial you have the total degrees d. We call it degree d. Okay, sometimes we use form to describe this homogeneous polynomial. For example, if you look at linear form, quadratic form, cubic form. Quadratic form is the last chapter in your LA1, right? Quadratic form, if you go and look at the monomial, they should have the degree d, like homogeneous degree 2, for example. Right? Those are called the quadratic form. Right? Linear form, if all of them are, for example, like terminology here, so for example, linear form, like x plus y, right? Okay, quadratic form, maybe x0, x1 plus x1, x2, something like that. Okay. Okay. Last one. Okay, before we break. So last one. So the last one is how to check something is homogeneous. Yeah, how to check a polynomial is homogeneous D. If you substitute your variable as a scalar multiple of t, okay, for all t, then you can actually pull the t out. Okay, how many t you can pull it out? D, power of D. Okay, power of D. But this is a if and only if. I guess one direction should be obvious, right? Homogeneous process. How to go backward? Okay, actually it's not too hard. It's not too hard. Okay, so in general, you can actually write your polynomial ring that split up as the direct sum of these homogeneous degree D subspace. Okay, they form a subspace. Is it clear why they form a subspace? If you have degree D plus degree D, you still degree D. Okay. Okay, what's the direct sum? Did I define it here? Yeah, I think we should. Okay, next time, I guess we'll do it. Okay, let me think. Will I do it or not? Yeah, I will do it next time. Okay, so from here, right, how to define a projective algebraic set? What do you think? How to define a projective algebraic set? Affine algebraic set, we just want it to be a zero set of polynomial in AN, right? Here, can I just take polynomial from Sn or not? Cannot, because I already showed you this motivation, right? So you need to consider homogeneous polynomial. Okay, you need to add one adjective. Okay, see you next week.